If you weren't here, you missed it. I forgot to turn on the recorder. I thought I had it on, but I either hit it and turned it off or something. So anyway, we're beginning here. Sorry about that. Let's go from current slide. Oh. Everything I did, you can't see anymore. But anyway, we did 25 degrees Celsius, 77 degrees Fahrenheit. Give me a good, reasonable degrees Fahrenheit. Just make up a number. Temperature in Fahrenheit.
75.
Say again? 75. So we're going to get close. Woo. I have to change everything back. Let's start with 75, that's what you said, degrees Fahrenheit. Okay? We want to get that to Celsius. We don't know what that would be up in Canada or down in Mexico or wherever we happen to be, not in the U.S. Okay? So, let's do our yuck. I didn't allow myself enough room here. We're going to put units here, numbers there. And we're trying to get to, well, we're not going to need more room. Okay. We're going to ultimately get to degrees Celsius. So, what unit goes top and which unit goes on the bottom? Always put the units in the place. Degrees Celsius on top, degrees Fahrenheit on the bottom. This way, your Fahrenheit cancels. Okay? So, what numbers do we match with this? How many degrees Fahrenheit is how many degrees Celsius, or vice versa?
5 to 9.
5 to 9. Dolly didn't sing that one. Okay. Now, this isn't going to go in as evenly as the other did. Boo has. But we don't quite do that yet. Sorry, I got out of tune. In fact, I think we wound up very close to what we needed to be. We don't want to divide that out yet because you see, we have to get to the same zero first. So before we multiply, we have to subtract 32 so we can get down to degrees Celsius. So what's 75 minus 32? 43 degrees Fahrenheit. That's what we cancel out. Okay? So multiply. Sorry. 43 times 95 would be 215 over 9. So someone pull out your handy-dandy calculator and see what that is. 215 divided by 9. That would be 23 point what? 0.8 degrees Celsius. Yeah. If 25 degrees Celsius was 77 Fahrenheit, 23.8, pretty close to 75. That makes sense. Okay, we just have started recording again. I've got to go clear my head because I am having more and more trouble talking, and that strains my throat even more. So that's why, in the formulas here, if you're starting with Fahrenheit, and we've got all my arrows again, this is that one, this is that one, and this is that one, okay? If you're starting with degrees Fahrenheit, you first subtract 32 degrees Fahrenheit from it, and then that's what you do with 5 to 9 to get degrees Celsius. If you're starting with degrees Celsius, which is starting at 0, you don't have to add or subtract anything. Then to get the degrees Fahrenheit, you do 9 to 5. So 5 degrees Celsius is Celsius cancels out, you get Fahrenheit. But then that gives you how many degrees Fahrenheit that is, add it to 32. Okay? So you subtract first, then multiply going one way, multiply first, and then subtract. Then add going the other way. All right. let me, I got to pause for a minute. That's not the one I use. And I think we're just about at the place where we can do example 4.1 and 4.2. So let me erase what I've got here. Any questions so far before I erase this? You see how this works? Okay. So, the average human body temperature is 98.6 degrees which? Fahrenheit. Okay? If that were Celsius, we would be in serious trouble. Okay. What is the equivalent temperature on the Celsius scale? So how are we going to deal with this? Again, I'm going to have to put my conversion over here. They do it on the other side. But what have we got to do first? Because you're starting in Fahrenheit. You got to subtract 32 because you got to get down to the same zero as Celsius. So that would be minus 32 degrees Fahrenheit. Okay? And then you do what? That's when you multiply it by your conversion factor, and you have to decide which one to put top and which on bottom. What do you think? You're trying to get 2 degrees. Let's see, can I get that? Yeah, I can get that out of the way. Okay. Oh, that was your cheat sheet, wasn't it? Okay. Trying to get to degrees Celsius. So what unit? Put your units in the place. What goes where?
Celsius on top.
Celsius on top, degrees Celsius on top, degrees Fahrenheit on the bottom. What's the ratio? 5 to 9. Okay. Sounds like how long this class goes. No, just kidding. Okay. So, let's do the math. 98.6 minus 32. What does that come up to? 66.6 degrees Fahrenheit. I hope nobody's getting too upset with that number. Okay, it's got a decimal in it. Okay. All right. Now, because I don't have a calculator handy, I'm going to divide 3 into this and 3 into that, and that would give me 22.2. But then I see, well, 3 will go into that as well, so that'll be a 1 there, and this would be a 7.4. Yeah. Then I take 7.4 and multiply it by 5, and I get 37. You can say 0.0, but you don't need it. 37. Well, you started with that. 37.0 degrees Celsius. Now, if you got calculators, it'll do all that work for you. Make sense? They just put 37. 37 degrees Celsius. So, someone said, do you have a fever? Oh, you're at 35. No, you're below normal. This is normal. If you're at 38, yeah, you have a fever. And that would be sort of significant. A lot worse than 1 degree would be here in Fahrenheit. But, because that's 1.8 degrees, remember? So, that's example 4.1. Let's do 4.2. All right. A bank temperature displays 20 degrees Celsius. Now, they say that's room temperature. That's on average about what room temperature is. What is the equivalent temperature in Fahrenheit? So now we're going from Celsius to Fahrenheit. So what are we going to have to do? This time I allowed enough room I can put my conversion in front. What units go where? Help me. We're trying to get ultimately to degrees Fahrenheit. Say again? Well, always put the units into place first. What unit goes where?
So what you're looking for goes on top, right?
The which? Yeah, what you're looking for goes on top. Degrees Fahrenheit on top, degrees Celsius on the bottom. That way you can cancel out degrees Celsius and left with degree Fahrenheit. Now, how many degrees Fahrenheit for how many Celsius? 9 to 5. You got it. Dolly Parton. Okay. But then what do you have to do once you get that conversion done? Because Fahrenheit has a different 0 point. See, this gets you to degrees Fahrenheit. Now you add the 32 degrees Fahrenheit, and that makes sense. So 5 will go into 20. How many times? 4? 4 times. Okay, 9 times 4 is 36 plus 32. 68 degrees Fahrenheit. Yeah, nice, pleasant temperature. That's what I have the cab of my vehicle set to, is 68. I don't like it too hot. I don't like it too cold either. And that's what they got in the book too, 68 degrees Fahrenheit. Now, let's talk about Celsius and Kelvin. Okay? Remember the deal here? If you're at Celsius, 0 Celsius, to get to 0 Kelvin, that's minus 273 Celsius. Kelvin, to get to 0 Celsius, you're plus 273 K. So whatever temperature you are in Celsius, subtract 273 from it to give you K. Whatever you are in Kelvin, add, no, I said it backwards. Whatever you are in Kelvin, subtract 273 from it and you get degrees Celsius. Whatever you are in Celsius, add 273 to it, and that gives you Kelvin temperature. So that's where they get that last, the last conversion there. Degrees Kelvin is whatever your Celsius temperature is, plus 273. Remember, Kelvin, I said it and I said it wrong. You never say degree. It's just K. Degrees Celsius plus 273 gives you K. That really should be 273 degrees Celsius. You'll have to get away with it. Okay? So, I actually said it wrong. Look at the lines just below that equation 4.3. A temperature of absolute 0 has never been reached. But scientists have cooled a sample of sodium to 700 nanokelvins, or 700 billionths of a Kelvin above absolute 0. Now, who in the world can measure a billionth of a degree Celsius? I don't know how they do it. Well, this is almost a millionth. 700 billionths is almost 1 millionth of a degree. Amazing. Okay. All right. Oh, sure. This one. Is that the one you wanted?
Yes.
Okay, sure. And remember, this is that one, this is that one, this is that one. When you're going from Fahrenheit to Celsius, this is what you use. From Celsius to Fahrenheit, this is the one you use. And Celsius to Kelvin, that's the one you use. Now, if you don't mind memorizing equations, you can memorize them. But to me, it makes a lot more sense to figure out why they are what they are. Before you can go Fahrenheit to Celsius, you got to drop the Fahrenheit down to 0, not 0 Fahrenheit, but so you're measuring how many degrees above freezing are you. Well, that's your temperature, Fahrenheit minus 32. That's how many degrees you are above freezing point of water. Because Celsius measures degrees above freezing point of water. So that's why you subtract first. And then because 5 degrees Celsius makes 9 degrees Fahrenheit, that's why you put it that way. I wish they put the units in. Now, the other way, this is already degrees above freezing point, okay, of water. So you get how many Kelvin Fahrenheit degrees that is above the freezing point of water. But the freezing point of water is 32. So you add this, because that's how many degrees Fahrenheit above the freezing point of water at 32 degrees Fahrenheit. That, to me, makes more sense than memorizing the formula. And then I just have to think about the other 0 degrees Celsius is minus 273 K. So you add 273 to 0, that would be your Kelvin temperature of the freezing point of water. Boiling point, freezing point of water. Okay. Ready for example 4.3? All right. The relationship between Kelvin scale and Celsius scale is found in equation 4.3. We just referenced that. And here they give it to us. Solving this equation for Celsius yields what? Okay, let's go back. They're taking this and say, solve that for degree Celsius. Solve for a degree Celsius. How would you do that? If you want to solve for degree Celsius, isolate degree Celsius. Subtract 273 from both sides. So here's the formula you get then. Temperature Celsius is equal temperature Kelvin minus 273. See, that's the one I would not put a unit on. Say K, okay? This is the one up here I would put a unit on and say degrees. Well, I've got the wrong. I would say degrees Celsius here, because that's temperature Celsius. Add degrees Celsius, you get K. This is K, subtract K, you get degrees Celsius. Just being a little picky there, okay? Oh, I'm sorry. I was not reading the problem right. Let's get out of that. Whoops. I didn't read the problem. I was looking at the solution. A science article refers to a temperature of 300 K. Okay, let me get my pen back in the right color. So your T sub K is equal to 300.0 K. Never put degree symbol with K. The A question here says, what is the equivalent Celsius temperature? What did we just do? How do you get from K to Celsius? This was Celsius to Kelvin.
You subtracted 270.
Okay, so you do T sub K minus 273 K equal T sub C. So this would be 300.0. I don't know why they put a 0.0 there. K, subtract 273. So you don't have, so that's not really necessary. What do you get?
27.
A little louder. 27 degrees Celsius. That sounds like it makes sense, because your scale for Celsius is always way less than the scale for Kelvin. Because Kelvin, 0 is way down there. Celsius is up here. Okay? The next question says, B part, what's the equivalent Fahrenheit temperature? Okay. The question I have for you is, do you need a conversion to get from K to Fahrenheit? Please don't. Now, this is a really dumb statement here, but how do you kill a blue elephant? I know you don't want to kill a blue elephant. How do you kill a blue elephant? With a blue elephant gun, of course. Okay, how do you kill a red elephant? No, you don't go buy a new gun. You swing him around by his truck till he turns blue, and then use your blue elephant gun. You don't need a new gun. Okay? So, when you're trying to get from Kelvin to Fahrenheit, don't come up with a new formula. First go to Celsius. You already have that one, and then use your formula for Celsius. Okay? So we've already done the Celsius, 27 degrees Celsius. So that's where we're starting, 27 degrees Celsius. How are we going to get that to Fahrenheit? What do we better do first? Okay. Yeah, get your units in place first. Degrees Celsius down here, degrees Fahrenheit up here, so you can cancel out degrees Celsius. And what was that ratio you said? 9 to 5. 9 degrees Fahrenheit for every 5 degrees Celsius. And this is one takes a little more work. That would be 63. 18 and 6 is 243 divided by 5. And that would be 28.6. Okay? That's degrees Fahrenheit. That's how far above you are, above the freezing point of in Fahrenheit. So you add to that 32, which is your
48.6, not 28.
Oh, I'm sorry. My brain's not working well. Okay. 48.6. Duh. And add to that 32, and what do you get? 80.6. Now, they're going to be real picky about it and say, well, sorry. And I really don't think they have any grounds for pickiness. They started with 4 degrees significant digits. These ratios are perfectly fine. This is even good to 3 digits. This could have been to 3 digits. This could have been, but they say 81. They round it to 81 degrees Fahrenheit, which is fine. I can't read 0.6 anyway, so that's what they say, 81. The last step is a round off. There's nothing magical about that. Okay. I'm running out of steam. All right. There is a good little blurb at the top of page 94. It's called A Closer Look. It talks about goosebumps. I've also heard people refer to that as another thing. I can't think of that other term they use for it. There is another term for it. And shivering. Why do you get goosebumps when you get cold, and why do you shiver when you get cold? It's nice little blurb there. Read it and see. Okay? But where we're going on page 94 otherwise is heat. 4.3, heat. All right. Here is the sort of their formal definition for heat. So they're going to use modifications of it a lot. They say heat is a form of energy transfer between two objects. Okay? I've often heard it called thermal energy. And that's not a bad definition for it. But that's not what they're calling it. Heat is always a transfer of energy. So when you say, oh, it's hot in here, you're not talking about how much heat is in the room. You're just saying what the temperature is, basically. Heat is a transfer of energy, okay, between two objects. This is talking about two kinds. External energy, which is total potential and kinetic energy of an everyday sized object, okay? Total potential and kinetic energy of an everyday sized object. Now, let's take that's the external energy. The internal energy is the total kinetic energy of the molecules inside the object. Okay, so you have two things. External energy. So let's say here we have this partial bottle of goo, okay? This is hand goo, okay? Now, its external energy is the total potential and kinetic energy of this. So how fast is it moving? What is its internal energy? I mean, what is its potential energy? How high above the floor it is? Kinetic energy, its temperature, that kind of thing. Okay? The internal energy is the total kinetic energy of the molecules in that. Okay? And that would be measured in temperature. This would be how much energy it has for its position, for its speed, whatever. The external can be transferred to internal, resulting in a temperature increase. Remember the last chapter we talked about James Prescott Joule. Remember, he was the one the unit for energy was named for. Well, he did some of his experiments were taking a very carefully controlled situation. I think it was water in a thing, had a thermometer in it, and he turned on an electric motor with a paddle on it that stirred the water. That is changing its potential and kinetic energy from an external energy thing, and that change resulted in a increase in temperature because it increased the internal energy. The internal energy that it had was Mendez. Okay. I've got a cold, I'm not upset. That's not what we call it. Okay, so external energy can be transferred into internal, resulting in a temperature increase. Another example, take your hands, rub them together while you're pressing, you can feel a bit warmer. You've changed the internal energy of it, changed the temperature of it by adding external energy to it, kinetic energy. All right, here the gal is pushing the table, I'll push the desk here, across the floor. Okay? Now, what did you notice here and there? There was noise, didn't it? That noise means there were vibrations. Vibrations meant there was friction. Okay? Because there was friction, I was producing a little bit of heat. Now, remember I said a thermocouple? If you had a very sensitive thermocouple somehow connected to, or very near the bottom of the chair, you would have seen a little bit of increase in temperature there. Because, sure enough, her external, or my external pushing on the desk, she's leaning down on it too, is creating friction down here, increasing the internal energy on the floor and on the bottom of the foot of the chair. All right. Now, this slide doesn't have it. I'm sorry, my throat's going on me. It's sort of what we were just talking about, but I don't see a specific topic in the book for this. Let's look at heat versus temperature. Temperature is just a measure of the hotness or coldness of an object based on average molecular kinetic energy, internal energy. Okay? Average molecular kinetic energy. That's what temperature measures. Heat is based on the total internal energy, okay? Total internal energy of the molecules, and not the average. See, there is a difference here. Let's do the experiment this way. Okay, I have a little thimble. You all know what a thimble is? These sewers in here. A little thimble full of hot water. Okay, I have a bathtub here full of hot water. Okay, which has the higher temperature. Depends on how hot the water is. It actually could be the thimble is higher temperature than this, but which has more heat? Yes, because the tub of water has a whole lot more water in it. Now, how could you tell that? Let me take a little sliver of ice and drop it into the thimble. You think the temperature is going to go down? Yeah. No, big time. I'll take that same little sliver, one identical to it, drop it in the bathtub of water. Notice any change in temperature? If you had a sensitive enough thermometer that would measure a few billionths of a degree, maybe you could, but otherwise no. Okay, so yeah, this had higher temperature, but that had much more heat. Okay, doubling the amount of anything at the same temperature also doubles your heat. And here's the example they give of this. And this is the illustration at the top of page 95, right-hand column. If you were a big coffee drinker, oh no, this is water, okay? But you like your water warm, like very hot, 90 degrees Celsius, just 10 degrees below the boiling point of water, pretty hot, okay? You have a liter of water there, or you have a dainty little demi-tasse cup of 250 milliliters of water at 90 degrees. Which has more heat? Absolutely. They're at the same temperature, but this one has more heat because you have more water. It would take 4 times as much ice to cool this to the same temperature as you would that. Okay? 1 cube here, 4 cubes there. This has more heat. So heat versus temperature. Now let's go back to heat again. And this is a little ragged the way they put this together. Here's another definition of heat. A measure of the internal energy that has been absorbed or transferred from another object. I remember before, a form of energy transfer between two objects. So here's the other way to phrase that. A measure of the internal energy that has been either absorbed or transferred from another object. Okay? I think they really meant 2 here, but that's okay. It could have been absorbed or transferred into internal energy change. There are 2 related processes here, and they go over these on page 95, right-hand column. Okay? You have heating, which is increasing the internal energy. That you're adding energy to it somehow. Or you have cooling, which is decreasing the internal energy. You're absorbing away the heat in it. Now we're going to talk about this a little bit later, but in a cooling system, I know you guys and some of you others have studied cooling systems. Some people's whole deal here. What's the first step in a cooling system? First thing that happens. Anybody? Say again?
What type about the system we're talking about? We're talking about like an air conditioning cooling system. We're talking about the radiator.
No, that's the air conditioning.
Air conditioning.
Y'all study that too, right?
Uh,
What's the first step in cooling?
You want to make sure you have your right pressure.
What?
Your right pressure.
Okay.
Pressure for your freon.
Right, okay. Got all that.
Got all
What's
that.
the first thing you do to it?
Condenser.
Okay, what does that do to it?
Cools it off. It changes
Okay,
the
before you can
liquid
cool it
to
off,
the-
is it the first thing you do, you pressurize the gas? What does that do? It makes it hotter. Okay? That's the first thing you do, you pressurize the gas. You have to, because the next step is to let it expand, and that's where the cooling comes. Right? So, you first have to add some internal energy, then you let it expand, and that produces the cooling. Now, what you do when you are air conditioning, you compress that, and then you try to blow that heat away. You want that heat as far away from the system as possible. That's what that big fan outside your house does. It's blowing the heat off when you have your AC on. And then you let it expand, and that draws the heat out of the house. We'll get into that more. So that's your cooling. Decreasing the internal energy. Generally, you have to increase it to begin with. So, what are your heating methods? One method is a temperature difference. Okay? If you're trying to heat something up, in the old days, and this was even before my time, so don't make any jokes about it, how they, in the big house where the lords and the ladies lived, someone hot bricks that they had kept by the fire, took them up and put them in the bed to warm the bed up before they came up to go to bed. Okay? What you're doing was a temperature difference. The bed was cold, they put the hot rocks in there to warm up the bed. Okay? So when the lady came up, she didn't get chilled, you know. So the energy always moves from higher temperature region to lower temperature region. So you've got to have a change of temperature for this to work. And the heat always goes from high to low, high potential to low potential. Okay? But there's another thing that can happen, and that's an energy form conversion. And that's a transfer of heat by doing work. Well, that's what I was talking about by the compressor. Yes? Oh, is it? Oh, shucks. Let's get this one slide down. That's what your compressor does. You're doing work on that gas, Freon, whatever it happens to be. We call it Freon. We don't use Freon anymore, but the refrigerant. You do work on that, compress it, make it hot, blow that heat away, and then let it expand, and that's where your cooling comes from. Okay? That's a real quick and dirty. It's not doing it justice. Okay? But that's an energy form conversion. Or you have a heat temperature difference. One or the other. All right, what's the next slide? Measures of heat. That's at the top of page 96. And that's where we begin next time. Measures of heat. Okay. So I'm going to put this on pause. All right, listen up now. I'm sorry about my throat and my voice. All right, this experiment is concerned with using your reference points, and we talked about that in class today. We talked about how they came up with different scales. We measure these, at least on Fahrenheit and Celsius, in degrees, okay? And they're different sizes, by the way. Today, we're going to be using almost strictly Celsius. I don't think, we will be doing some things with Fahrenheit, but that's later, okay? Now, what was the problem with Galileo's first attempt at a thermometer? It's what? The air pressure also affected it. So therefore, before we do too much tonight, we need to see what our barometric pressure is, because that may affect some of our readings. I doubt if it's going to be much, but let's see what it is. Anyone got a phone or other device you can get the barometric pressure for Bessemer, Alabama, as close to right now as you can.
I got 29.96.
Okay, that's 29.96. What units?
5 inches of mercury.
Inches of mercury, exactly. Okay?
Can you turn the board a little bit?
What's that?
The board. Can you turn the
Oh,
board?
okay, sorry. How's that? I don't want to erase their stuff.
Are we supposed to write this down somewhere?
Okay. Where we will be writing it ultimately, but leave plenty of room for adjustment, is barometric pressure on page 152, and it'll be the same for trial 1 and trial 2. In fact, on trial 1 and trial 2, name that temperature 1, or thermometer 1 and thermometer 2. At the top of that page, make that thermometer 1 and thermometer 2. I gave each team 2 thermometers. You identify which one is which. Like the guys here on this table, one of them's yellow and one of them's white. See if you can figure out something. Yeah, yellow and white. Okay. Yours are both white, or they both got red in it, or does one have silver? Okay.
Mine's in sulfur.
Okay. No. Why don't you say yours has marine? Okay, yours is marine. How about yours? Take the nose out. Okay, that's good. All right. So you know your thermometers. So which one's which? So under barometric pressure, write 29.96 inches of mercury. The double tick is inches. Okay, but if you read on, it says here that atmospheric pressure, normal 1 standard barometric pressure, is found as the atmospheric pressure that will support 760 millimeter column of mercury. So this is the barometric pressure actual. This is, yeah, okay. The purple, but it probably is going to be so thick. Okay. Let's see how it does. Yeah. Barometric pressure actual. Normal barometric pressure, I'll put BP normal. That is 760 millimeters of mercury. Okay. They're both mercury, no problem there. We have to convert our inches to millimeters. So this will be 29.96 inches. I'm going to write IN, so that's easier to see. Times blank blank equal blank, and we might need, y'all might need 2 sets of blanks. You might not, we'll see. Okay. I'll do an extra set just in case you need it. Equal blank millimeters of mercury. Okay. Now, how do you get from inches to millimeters? Anyone know a conversion right off the top? If not, can you get something in between the two? Centimeters. Okay, let's go from inches to centimeters. What are you going to put on top? What's on the bottom? Centimeters on top and inches on the bottom. Now, what's the conversion between centimeters and inches? Okay. I'll tell you exactly. 2.54 centimeters, 1 inch. Does that look right? Okay, 2.54. That, by the way, is exact. They've defined it that way. So that's going to get rid of inches. Okay, now we got to get from centimeters to millimeters. What is going to go, which going to go where?
centimeters on top. No, centimeters on bottom.
Centimeters on bottom and millimeters on top. Okay, that's supposed to be millimeters. Okay, what's the conversion there? Anyone know? Oh, come on.
One at the bottom.
Okay, one at the bottom. Okay, that's going to be right. So look at your rulers. Okay, don't break your rulers. Okay, look at your rulers, and you see the big numbers here are centimeters, and the little tick marks are. And how many of millimeters are in a centimeter? Count them. How many? 10. It's metric. So 10 millimeters, 1 centimeter. Now the centimeters go out. Okay? So do your multiplication there. 29.96 times 2.54 times 10. How many millimeters of mercury is that?
760.
Say again?
760.98.
Let's just say 761, okay? All right. We're 1 millimeter, 1 silly millimeter larger, okay? Y'all don't remember that. Virginia Slims. No, something like that. Okay, 1 millimeter above normal. Okay. Now, if you read on, front page, a boiling point, no, an atmospheric change that increases the height of a column of mercury will increase the boiling point by 0.037 degrees Celsius for each 1 millimeter of height. So this is equivalent to 1.0 millimeters of mercury. And that's what we've got. So we're going to increase or adjust our reading by 0.037 degrees Celsius. Okay? Take a look at your thermometers. Any of you think you can measure 0.037 degrees? No way close. Okay? But we're going to do the calculation instead. So turn to your page 152 again, and your barometric pressure where you wrote 29.96 inches of mercury, also write in that same block 761 millimeters of mercury. Okay? Deviation from normal plus 1 millimeter of mercury. Okay? But I think the deviation they want here is 0.037 degrees Celsius. You're not going to be able to measure it, but that's how far off you are. Say again?
That's deviation from normal?
Yes. On both blocks there. Deviation from normal plus 1 millimeter of mercury, 0.037 degrees Celsius. No one's going to be able to measure that. Okay? Now, you guys that were in Physical Science 1 class, you remember we said they're right on the equator because of all the heat and stuff. The water rises, lowering the pressure there, and comes down about 30 degrees north and south of the equator, raising the barometric pressure there. That's right where we are. So we're just at or slightly above barometric pressure. I would have sworn that being at this elevation, which we're not a great elevation, we'd be a little less than that. But no, bet you down on the Gulf of Mexico, in Mobile and Gulf Shores and places like that, they're a little bit above this. We're right at, almost always right near normal barometric pressure. Okay, we got that going. What we're doing, I'm killing time, waiting for our water to boil. And it's getting close, but it's not quite there. So let's continue with the lab. Now, where we're supposed to start is with the ice. I forgot that. I thought we started with the other. So we got time. So get your two thermometers that you know which one's thermometer 1 and which one's thermometer 2. Your whole team knows that. Put them in the beaker. Now don't get them crossed over with everybody else. Your team number is somewhere on your thermometer. So know what yours are. Put them in and let them come to equilibrium. When it looks like they're at equilibrium, you can go sit down for a few minutes and we'll talk a little more. When you're confident the mercury's going down, or mercury or alcohol is going down as low as it will, then let me know. Go back to your station and we'll talk just a little bit more. Okay. Think it's going as low as it'll go? Okay. Everybody? Both thermometers? Okay. Now, what we're going to do next is, after we measure the temperature at freezing point, we're going to put it in the boiling water, and it's getting close to boiling now, isn't it? All right. Now, let me ask you a question. Tell me what you think. With the room temperature being warmer than the cold water back there, do you think the ice is melting now or staying the same? It is melting, okay? So, it's been several minutes since you saw your thermometers. Go check them again and see if the temperature is the same or if it's dropped, because you said the ice was melting. This time, take your paper because you're going to record your temperature. Now, when you pick up your thermometers so you can read it, be sure you leave the bulb in the ice water. Pick it up just enough to read. And you're going to put this on observed melting point, thermometer 1 and thermometer 2. Okay, again, be sure when you read your thermometer, you can pick it up a little bit, but hey, make sure the bulb stays in the water. Hey, that won't give you a good reading out of the water. Oh, you already got it? Yeah. Okay. All right. You took your reading while it was in the ice water, though, right? Okay, good. All right, everybody measure that. Now, what should the measurement have been for ice water? Say again? Yeah, but that's Fahrenheit. What would it be? It should be 0. Were any of you right at 0? No. Okay? If you were below 0, you had a negative measurement error. If you were above 0, you had a positive. So on the second line, under thermometer 1 and thermometer 2, record your measurement error. You recorded your temperature in the first block, your measurement error in the second block. And guess what? It's the same thing, aren't they? Because 0 is your reference. Okay? Now, if everybody's got those measurements made, the water in the second beaker is boiling. Not quite as heavy as it was a while ago. So take your thermometers, know your thermometers, and put them into the boiling water. Be careful, don't get burned. Know your thermometers. Okay? After you put them in, it'll probably stop boiling just because the thermometers are cold. It should start boiling again, so we gotta wait a few minutes. Now, be sure you wait till the water starts boiling again. It hasn't started again, has it? Because the thermometers were cold, so I've got to turn it up maybe a little bit more. Okay. While y'all are waiting for the water to boil, I'm going to I'm going to put this on pause for now. Remind me to, okay, a quick review. You measured your freezing point. You measured your observed melting point, your measurement area of the melting point for both thermometers, your observed boiling point for both thermometers, barometric pressure we got at the beginning, deviation from normal we got at the beginning, accepted boiling point, that was 100 plus your 0.037, which is basically still 100, and then your measure area of your boiling water, okay, boiling point. Okay, so where we are now, procedure 1, you did the lower fixed point. That was your ice. Procedure 2, you did the upper fix. Now, we didn't have a fancy setup like this, but we did it. Okay. Now, we've done 3 and 4 now. If you're not doing a second trial, you use 2 thermometers. Now, let's turn over to page 151. Using the data from your better thermometer, you had 2 thermometers. The one that was more accurate, if either one of them was better than the other, closer to the normal, closer to accepted. Were there? Huh?
We had one.
One was closer. Use that one. Okay? Now what you're going to do, you're going to make a graph plotting the Celsius temperature on the horizontal axis and the Fahrenheit temperature on the vertical axis. So what you're going to do, you're going to set it up letter mode. Celsius down here, Fahrenheit up here. Okay? Celsius, you got to go about 0 to 100, right? So 0, 20, 40, 60, 80, 100. So each one of those blocks is that. Did any of you have anything below 0 on your melting point? Were you? Or you all started at 0 or above? Okay. So 0, 20, 40, 60, 80, and 100. Okay. Now, what we're going to do next, from your best, okay, here we go, the page, I got lost on the pages, page 151. What you need to do now is calculate from your best thermometer, your better thermometer, because I only had 2. So go back on, keep turning the wrong pages, page 152, and under the better thermometer, then you need to, by your observed melting point, calculate what your melting point was in degrees Fahrenheit. You registered that in Celsius. What you need to do is register in Fahrenheit. And you know the formula for that? Yes, good. I'm going to erase these if that's okay, all right? All right to erase? Yay? Okay. Okay.
Let's say two, because we didn't-
Does anyone need help on how to convert Celsius to Fahrenheit? Want me to write it up here? Okay. You know your degrees Celsius. I'll let you fill in whatever that is. Okay? What you're going to do is multiply this by blank blank. What unit goes where? Set degrees Celsius on the bottom, degrees Fahrenheit on top, and what's the number that matches here? Say again? 9 to 5. You got it. Dolly Parton. Okay. Now, that gives you how many degrees, because your Celsius goes out, and this measurement was how many degrees you are above zero, above the freezing point, melting point of ice. Okay? So this is how many Fahrenheit degrees you are above that. Well, what is the Fahrenheit reading for the freezing point of water? 32. So add 32 to that. Because you canceled out your degrees Celsius, so your degrees Fahrenheit, and that will give you your degrees Fahrenheit. Okay? So in the same block that says observed melting point, do your calculation here for your degrees Celsius, whatever that was, and convert it to Fahrenheit. Write that in the same block by your better thermometer, under your better thermometer. Okay? Everybody got it?
Okay, ours is 1 degree, so what is that?
1 degree. Put 1 degree here. So 1 times 9/5 is 9/5. Okay? Convert that to a decimal. 9 divided by 5 is what? 1.8. Add that to 32. That's 33.8. Right? Okay. So everybody should be fairly close to that. Are you? Can you have you up around 85? Good. No, I'm just kidding. Okay. All right. Okay. Somewhere around the low 30s. Right? Okay.
We go about 20s on the Fahrenheit side?
Okay, we'll do that in just a second. Yeah, you're absolutely right. That's exactly what we're going to do. Okay? Now, okay, listen up. Do the same thing for your observed boiling point. Okay? On your better thermometer, whatever that reading was, do that. And do 9 times that divided by 5, add 32 to it.
We started in Celsius. Yeah, let's start.
Okay, everybody got your degree Fahrenheit? Do you? Okay. Now, so now you have 2 points. You have a, whichever your better thermometer was, you have a Celsius boiling point, and you have a freezing point. Okay? And you have a Fahrenheit that corresponds to each one of them. So on the Fahrenheit scale, as Mark was saying, we need to use start at, now, okay. Did any one of you have a melting point Fahrenheit reading of less than 35? Yeah, some of you did, 33.8, okay.
We did. I don't think that something was right with our thermometer measurement or something, because we got a negative. So that can't be.
Whoa, wait.
Yeah, that can't be.
Wait, I don't even see your observer. Wait, you got negative 30 and negative 22?
That's what he said. You brought him back, and that's what you said.
No, you came over there, and that's what you said.
Wait, okay. All right, where are your thermometers? Oh, you don't know which one. Can you recognize them?
Yeah.
What team were you?
2.
2. Two. What's that? What? Okay. Were these your 2?
I think
Stop
so.
for a minute. Ice water, still ice water. This doesn't even read minus 30. See, it only goes down to minus 20. So you can stop it at minus 30. Okay, well, you're a team. Work together. That's why I asked before, all of you around 32. Oh, man, that knew that. What's happening?
About 3 or 4.
This is a weird, this must be. Wow, what is it? Huh? What was your, what was that?
80 degrees Celsius.
Yeah, this is awesome. Wow. So that reading was right. I'm really giving, these are all thermometers that have been used. This one, I guess, has gaps in it. So I don't put this in, this one has mercury. See what happens. She said no one likes the dust.
This one is the Celsius.
What?
This is the Celsius.
What?
Oh, yeah, you made one.
They don't have any over there. I want to go to our essence.
Now we have some.
Wait, I needed to
You like some?
heat temperature.
You need to do this one. No, oh, you got, what did you get before?
80 degrees Celsius.
Okay, for those who are ready to do your plotting of points. Okay, we've got a little bit of a problem with Fahrenheit. Even if we put 30 at the bottom down here and go up by 20, that would be 30, 50, 70, 90, 110, 130, 150, 170, 190, 210. 210. That wouldn't go high enough. So what we're going to have to do with Fahrenheit is go by 30s. So let's do 0, 30, 60, 90, 120, 150, 180, 210, 240. Okay?
So yeah, I just wrote whatever.
Did it start boiling again?
Yeah, I got it.
Yeah, but was it boiling? What'd you get?
97.
Okay, it wasn't boiling yet. See, it hasn't really started boiling. Just again.
Lower pressure equals lower water point. As the water is boiling at higher temp. The other reading Shakespeare. Yeah, I know it's
Put my shoes in because then you're going to see that.
This block right here.
Oh, yes.
Does that mean like the formula got?
All right. So everybody has, okay, did you get your Fahrenheit scale? As I said, start at 0 at the bottom and go up by 30. 0, 30, 60, 90, 120, 150, 180, 210, and 240. That will get you everything you need, okay? Now, with those numbers on there, plot your melting point, Celsius versus Fahrenheit, and then plot your boiling point, Celsius, Fahrenheit. Okay? Then every team has at least one ruler. Yeah, I think you have at least 2 rulers. Some of you have 3. If you can, draw the best straight line you can between those 2 points. You don't have a 2 points, so it's going to be a straight line. Okay? What's that?
What are we?
Okay, you're plotting the 2 points. You got your scale set up? So the first point is 1, 3. This is
Oh no, we won't go back. I already did the math for this one, so. Yeah, you're right. Okay.
All right. Well, then,
Yeah.
this one,
Oh, okay.
1 degree Celsius here.
Okay.
Has everybody plotted their 2 points?
What were we putting for our Celsius?
Okay.
I'm a little behind. For the Celsius here.
Oh, yeah, Celsius here. And it's 0, 20, 40, 60, 80, 100.
Alright, put it back there.
It is 1 on the Celsius and then 33 on the Fahrenheit. And then not sure how it's
Has everyone calculated your slopes now? Slope is rise over run. You only got 2 points, so it's easy to calculate rise over run. Okay?
Oh wait, then we just combine those two? Each within a one? Oh, we do. We combine the Fahrenheit and the Celsius. So it's 1 point.
Celsius on the horizontal scale, Fahrenheit.
Yeah, we figured it out now. So 22 Fahrenheit, 100 Celsius. And then go up to 2.
Celsius.
What are we supposed to be plotting?
Okay.
We're a little confused on that.
Where's your calculations? Okay. Where are they now?
He's got my pen.
So 4 degrees Celsius here. 39.2 Fahrenheit. There's your.
Oh, okay, so those are the coordinates.
Right. This is on the horizontal, this is on the. This is
The 100.
horizontal. Actual measure.
Or what?
Observe right here. 100.
Okay.
This way, the problem in this side. You just swap them.
Okay. Everybody plotted the 2 points. Draw them to straight lines. Are you working on calculating your slopes? What you getting?
Oh, I'm working on this.
Oh, I see. Slopes are slow coming, huh?
I'm trying to remember how we did that equation, like we did with the last class, and we tried to figure out.
Slope, rise over run. Rise is the difference in your y here and your y down there.
Yeah.
You got an exact value here. Whatever that was, minus whatever that was. Okay? Your Fahrenheit temperature, the difference in those, divided by your run is your Celsius temperature. Whatever this one was, minus whatever that one was.
So I subtract my Fahrenheit from each other and subtract my Celsius.
That's it, exactly.
And so
And then divide
the,
Fahrenheit by Celsius.
I didn't feel like counting all that. Why you do it? So the first one is 133.
Okay.
Fine.
Anyone got value of slope yet?
Oh, yeah.
Okay.
But for this one, you said it was this minus this, right?
Yeah, no, sorry, I'm not.
So, I don't know. Okay. And then where do we put our slope?
Okay. Okay. What is, on page 151, that's where you put your value of the slope, number one. And the question is, what is, okay, first, what is the value? What did you calculate it to be? Anyone want to volunteer? Say again?
Calculation.
Whatever your slope was.
11 over 20.
Okay, get it down to a decimal.
5.5.
Whoa. Let me see how you do that.
Or not 5.5. It's 11 over 20. Yeah, 0.
Say again?
0.55.
Wait, no, you said 11.
11 over 20. We went up 11 over 20. 2 points. It is.
We know X.
180.
So this is 180 minus 60. That sounds like
Yeah, then you 66. 166 over 100. Make that into points smaller. So like
60 this way. 60. 120
that way. 66.
How much?
66.
Okay, it's 120 divided by 66. Okay, sounds good. Okay. Everybody got a slope?
No, we're still trying to figure out how to do that.
Okay.
We tried to Google it, but it didn't help.
Difference here. Fahrenheit.
So it's 33 and 2.
Difference. Fahrenheit was. Oh, there you go. This is that. This one's that.
So we did that.
Whoa!
He did it right, but I thought it was wrong.
Oh, well, obviously.
Right. You subtract the two Fahrenheit from each other, and you get that, and then you get the difference between the two Celsius, and you divide it by 6. You put that in number 1 on page 1.
Tell me what did it take?
You did right.
30 on
Yeah.
the change in the these thing, okay? What is Fahrenheit change? Here.
So 180.
Okay.
You made it like that.
I'm gonna show you.
180 over.
Those are two Fahrenheit. And you subtract the two together.
Okay.
No, you get the 187, yeah. And then you subtract the two Celsius from each other, you get 104.
Okay.
Divide 187 by 104.
Has everybody got a number for number 1 on page 151? Everybody? Okay. Now, the next question is, what's the meaning of that slope? How did you get that? What was your eyes?
187.
Yeah, but what did that represent? Change of Fahrenheit over change of Celsius. Okay, very good. What was your value of your y-intercept? I think all of you put your 0 for the Celsius down at the bottom corner, right? So that's where your y-intercept. What did you read your y-intercept on this scale to be? Say again? Whatever you read yours to be. Your y-intercept, where's the line?
Oh, we're across right here? No, it comes out. Yes, yeah, it'd be 32. Because it crosses the 0.
What's that was on the y on the vertical scale? What's your vertical scale represent? Fahrenheit. Oh my. Okay. Now, all right. The slope-intercept form of an equation is y is equal to mx plus b. Now, what does the m stand for? What does the b stand for? Y-intercept. Okay? What is your y on your scales? Your vertical. Degrees Fahrenheit. So that represents degrees Fahrenheit is equal to, what was your slope? 1.8. What's your x scale measuring? Degrees Celsius. And what's your b?
32 degrees Fahrenheit.
Okay, somebody said 32. Now, what does that look a lot like? It's what? That is your equation that you used to convert here, wasn't it? Because 9 over 5 is 1.8. So you've just shown one way that you could get your equation for conversion. Graphically, you came up with the same equation as you did numerically or algebraically. So what is the meaning of this equation? That's your
Conversion.
Celsius to Fahrenheit conversion. Exactly. Now, this next little thing is just one little demonstration that we're going to do. And I see some sleep coming out there. So, and when everybody's finished what you're doing there, we'll do this demonstration. What's that? What's that? Yeah, there is sleep coming out there. So when everybody's finished, you want to gather around so you can see it, but if someone's still writing, you let them know. What I've done, I got some of this hot water that was almost boiling, put it in a little bit in the Coke can, a clean Coke can, and put that back on, and it seems to be boiling. You see steam coming out, right? So what I'm going to do is take this, and explode. What happened? Imploded. Why? Certainly was a temperature change. I think it was a little more than that.
Pressure.
Say again?
Pressure.
Yeah.
Pressure is what you said.
The pressure. There was definitely a pressure change. Okay? Now, why was there a pressure change? It had to do with the temperature change. Why?
The Chinese over there.
Yeah. What was in here, boy, it actually punctured the can. Okay? All right? What happened here, you had very hot water and steam inside the can, all right? That was water vapor taking a lot of volume. When you turn it over into ice water, suddenly that steam condensed to form water again. Well, water takes up much less volume than steam, so suddenly you had, like you said, the change of pressure. You also had a change of phase from gas to liquid, and actually atmospheric pressure did that to it. Because the pressure inside was way less than 1 atmosphere of pressure. So, think you're not under a lot of pressure? You got 1 atmosphere. Okay? What you created in there wasn't a vacuum, but something a lot less. Did all itself. Okay, this is the invitation to inquiry at the bottom of 151. It says, explain what happened. It says in terms of Charles Law, Boyle's Law, and molecular point of view. Don't worry about Charles and Boyle, but just do sort of what what we described from the molecule. Okay? However you want to do that. Any of you are interested in negative 1 or 5, negative 5 degrees in there right now. This one.
Oh, yeah, I just haven't done 3 or 4.
All right, remember you do have to question it. Turn back
Yeah,
to
but the
page,
results, I'm trying to hold it over 135.
turn back to page 149. Don't forget to do these questions. I should have taken my computer back there. I forgot to, sorry. On page 149, remember at the very beginning, I asked you, did the temperature change while the ice was melting?
Yes.
Is that what you answered before?
I mean, it's melting, doesn't it have to?
Yes.
Hey, remember I said put it in the ice water and come back. We did a few things. I went said go back and see. I said, did the temperature change any? But you did. You told me it didn't. And but you said the ice was melting. Okay? It says offer an explanation for that observation. Now we haven't quite gotten that far in the text yet, so I'll tell you that one. And it's something we said in class, but whether you picked up on it or not. Anytime that you have ice and water at the same location, they've got to be at the same temperature. And the melting point is that temperature. So, in other words, when ice is melting in the presence of water, it's doing a change of phase, not a change of temperature. Okay? And we'll talk about that in class on Tuesday. Now, how about number 2? It says, describe how changes in the atmospheric pressure affect the boiling point of water. Now, we didn't have any change, in ours, but how would it?
Higher atmospheric pressure has the water boiling at a higher temperature.
What's that again?
The higher atmospheric pressure has the water boiling at a higher temperature.
Okay, and why do you think that is? Because you have more pressure keeping the water as water, because higher pressure keeps it there and water has a harder time escaping. That's why you put your mom or grandma, did they ever use pressure cookers? And the reason is under pressure, you can get to a higher temperature, you cook the food faster. Any of you ever do any hiking in high mountains? Oh, you have. Did you do your own cooking up there too? Oh, shucks. If you had, you look at your food, and if you're at high elevation, they say boil it longer. because the water will boil at a lower temperature at a high elevation because you're under less pressure, because you're less atmosphere above you. So therefore, you have to cook it longer to get it to cook. Water boils at a lower temperature, and you need a pressure cooker there to get it to cook right. Okay? But that's why. The greater pressure keeps the molecules from escaping as fast, so it increases the boiling point of water. Whereas at a lower pressure, they escape faster at lower temperature. Do you think you can make water boil at room temperature?
Yeah.
How?
Take it up high enough for the boil right
Okay, I don't think we have any mountains that high. Here's what you do. Put it, what'd you say? What did you say though? Oh, I thought someone said put it in a vacuum. If you start taking pressure away, a vacuum pump, start pulling pressure off of it, all of a sudden you'll see the water start boiling. Because it boils at room temperature then, because there's very little pressure on it. It won't be hot, but it'll be boiling. Okay? Now, number 3, this team should be really good at this. Account for any differences observed in the melting point and boiling point readings between the two thermometers, or between what was expected and what you actually read. Say again?
100, like, you don't like the difference, like 103 degrees Celsius.
Okay, now why was that difference? Let me give you a couple. These were cheap thermometers, and they were old thermometers. What did you find out? One of them was completely out of calibration. It didn't used to be, so something's happened to that thermometer. So the calibration was bad. Remember when I had you taking mass measurements, what I always said you did first? Zero the scale. So make sure you're calibrated as close as you can get. With the thermometers, you have no way to zero the scale. They're stuck, okay? Their scale was a minus 20 or something like that, yeah. Way off, okay? Number 4, how would the differences determined in this investigation influence an experiment concerning temperature if the errors were not considered? What if you just took the thermometers at face value and said, yeah, that ice water's at minus 20? Be totally wrong. Your measurements would be off. You may come to wrong conclusions. All the kinds of stuff y'all are starting to do, right? Yeah. Any errors that you don't account for come back and bite you someplace that you don't want to be bitten. Number 5, if you answer it any way whatsoever, you get credit. If you leave it blank, you don't, okay? So answer it any way that you desire. Questions? You know, I forgot to call roll the second time. Let me call it now because you've all been here. Logan's here, Jay's here, Ethan's here, Amanda's here, Jonah's here, Patrick's here, Thomas is here, Frank's here, Mendez is here, Mark's here, Diamond's here, and Rand's here. Patricia still hasn't come in. All right. Now it's 6:45. That means you're going to have a full hour to work on your test if you want to. If you haven't finished your formula and equation sheet, you can be working on that. Would you rather go back to the classroom? I think so. These stools are not that comfortable, are they? Are there any questions before I shut this down? Okay, I'm going to start uploading.